field, the electric field is 300 nano or Newton coulombs. The charge that we're going to move in that positive charge, okay, so this is a positive charge. We know that we're going to have to do work in order to get it to go that direction, because the positive charge, remember, light charges repel, so it's going to want to jump out the other distance. So we want to find the change in potential energy. So based on what we've been doing, my change in potential energy is going to equal negative of the charge times the electric field times my change in distance. So if I did this another way, this is minus QED, where I get my change in distance. So I have that particular part. My change in X is going to be my X final minus my X initial. My X final is 0.5 centimeters. My X initial is 3 centimeters. So my change in X is a negative 2.5 centimeters, or it's a negative 0.025 meters. So I have my change in the right units. So now I can just plug and chug into the equation. So my change in potential energy is equal to minus QED, which is going to equal minus 1.602 times 10 to the minus 19. My electric field is 300 Newton coulombs, and my change in distance is that right there. Can't write it on my piece of paper. That's my change in distance, and when I plug that into the calculator, this is a negative, that's a negative, so I end up with a positive answer. And I get a number that's 1.2015 times 10 to the minus 19 joules. So if I look at how I've got my units, this is charge is coulombs, my electric field is in Newton coulombs, and my distance is in meters. Coulombs cancel, Newton meters, and I get joules for my energy. So that gives me my change in my potential energy working with that electric field. So that's one of the types of problems that you have from homework. Another type that you have is find the electric potential due to a collection of charges. So we're going to give you a collection of charges. I'm going to give you an 8 microcoulomb charge here. I'm going to give you a 2 microcoulomb charge there. Give you a 4 microcoulomb charge here. And we want to find the potential at this point. We're given that this distance is 3 centimeters. This distance is 3 centimeters. We're given that this distance is 6 centimeters. And this distance is our 6 centimeters. And we want to find the electric potential at that spot. So one of the equations I have for electric potential looks like this. K, Q over R. My electric potential is a scalar value, but I can sum up the electric potentials just like I can sum up my electric fields. So my electric potential at P, so the total at P, is going to equal the electric potential due to the 8 microcoulomb charge plus the 2 microcoulomb charge plus the 4 microcoulomb charge. I don't necessarily have to worry about the direction in this case like I do with my electric field, so I don't necessarily have to break it out into components, but I do have to know these individual R's. I have to know those individual R's in order to solve it. So I'm going to do that. I'm going to calculate my 8 microcoulomb one. So if I go to that point, that's going to be K, Q over R. That's going to be 9 times 10 to the 9th. And this is like my, that's my Coulomb's law constant. My charge is 8 times 10 to the minus 6 coulombs. and my distance away is 0.06 meters. Because I have to convert centimeters to meters, so I get that value. And when I do that, I get 1.2 times 10 to the 6th, and this ends up being volts. 1.2 times 10 to the 6th volts. Then I will do the next one. I'm going to do the 4 one next, because it's the easier one to do. Still KQ over R. That's my 9 times 10 to the 9th for my Coulomb's law constant. My 4 times 10 to the minus 6. Divided by, now I'm only 3 centimeters away, so I have to do the 0.03, and that's in meters. And when I do that, I get 1.2 times 10 to the 6th volts. The trick comes on the next one, 2 microcoulombs. Still have to do KQ over R, but I gotta know what that R is, and that R is this right here. So this is the R for the 2 microcoulombs. And I can solve for that.
I'm going to ask if you could slow down this time.
Okay. And I've got my R, so I can solve for R. And when I solve for R, I can use my Pythagorean theorem. So R is going to equal the square root of 3 squared plus 6 squared. So I end up with the square root of 9 plus 36. Gives me the square root of 45. And it gives me, when I do that, square root of 45, I get 6.7 centimeters. So this is the R2 microcoulombs, 6.7 centimeters, and I get 9 times 10 to the 9th, my Coulomb's law constant, my 2 times 10 to the minus 6 to get it into coulombs, because it was given to me in microcoulombs. And then I divide by my distance, and I have to convert from centimeters to meters, so that gives me 0.067 meters. And when I plug that into the calculator, I end up with 2.69 times 10 to the 5th volts. So now, the voltage total is going to equal my 1.2 times 10 to the 6th.
Can you put a breakout, please?
Is that up? Is that good? 1.2 times 10 to the 6th plus 1.2 times 10 to the 6th plus 2.69 times 10 to the 5th. And when I add those together, I end up with 2.67 times 10 to the 6th volts. So doing my voltages is a little easier than finding my electric fields, because I only have to know that distance away. I don't have to know all of that, the x and y coordinates in order to get there. I only have to know how far away they are. So that's what, so if I'm looking for the potential at this point, I just can sum up the individual potentials. I can still use the superposition principle, and I can still sum them up. But now let's look at what happens if I change my charge distribution and I put a negative charge in there. So I'm going to, instead of this right here, let's make this a negative 2 microcoulombs. So if I make that a negative 2 microcoulombs, I'm still going to add the velocity, or the potential total is equal to the 8 microcoulombs plus potential for the 2 microcoulombs plus the potential for the 4 microcoulombs. I'm still going to do the same. My values are the same, so 8 microcoulombs. We didn't change anything there, so that's my 8 microcoulombs. So that's going to equal 1.2 times 10 to the 6th volts. I didn't change anything for the 4. Okay, didn't change anything for the 4, so that's 4 microcoulombs is equal to 1.2 times 10 to the 6 volts. So I haven't changed anything there, but I did change this one. I did change this one, and I changed it by making that a negative charge. So this is going to be 2 microcoulombs. It's going to be my 9 times 10 to the 9th, times minus 2 times 10 to the minus 6 coulombs. I'm still the same distance away, so I get my 0.067 meters, and that's going to give me a negative 2.69 times 10 to the 5th volts. Still going to do the same procedure that I did before. Make sure I have a piece of paper under my piece of paper so I don't mark up the little tablet. So now I get the volt total is equal to 1.2 times 10 to the 6th plus 1.2 times 10 to the 6th minus 2.69 times 10 to the 5th. All of those are in volts. And when I plug that number into the calculator, I get a number that's 2.13 times 10 to the 6th volts. So before, when we were doing the electric fields and we were doing the forces, we had to look at whether or not I had an attractive force or I had a repulsive force. I had to put everything into the vector components. This time, I can use my voltages, and I do have to keep track of whether or not I'm positive or negative in order to determine my potential at that spot. But it certainly makes it a whole lot easier in order to get to solve the problem. And I think you've got some homework problems that look a lot like this. You may have triangles, you may have other point distribution charges. So when you start thinking for the test, okay, when you start thinking for the test, and knowing that a test will be coming up in the near future, okay, knowing that the test will be coming up in the near future, you know what's likely to be on the test. You're likely to have a force problem, where I'm going to use Coulomb's law, Q over R squared. Because we've done problems like that in class, we've done problems like that in homework. We're likely to get my electric field problem, which is KQ over R squared. Again, I'm likely to have to break up my components associated with it. And remember that the force is also equal to forces, the electric field. I do my force divided by Q. Yep, that's right. That's equal to E. Didn't want to mess up here. That force is equal to QE. So when you get your problems, you may be given an electric field, you may be given a force and a charge, you may be able to do the simple way to do the problem. Okay? So you're likely to see a problem that looks like that, and you're likely to see a problem that deals with the voltages and the electric potential using this kind of a problem or the kind of problem that I did earlier. So those are things that you're likely to have. And I think those are on the quiz right now. The quiz on electric fields is in there, and that's going to be the Coulomb's law one and the electric field. Let me see when it's due, because I don't remember when it's due. It's available when we get 2 attempts. It's displayed after yesterday, and it's due at midnight on the 24th, which is Saturday night. So your electric, so the quiz, and where the quiz is, just so you guys know, I go to the computer. It's in week 6, and you've got Monday's classes on there, and I actually got the PowerPoint loaded yesterday. So the PowerPoint that we've been working with is also loaded. So you've got everything right there and looking at the electric potential. All right, so do one more problem and then we'll play with building a capacitor. Okay, go back to the document again. All right, so on Wednesday, okay, so today is Wednesday. So on Monday, we talked about doing a circuit. And we said that in my circuit, that this represents a capacitor. This represents a battery. And this is where Ben Franklin gets us a real pain in the tushy, okay? Real pain in the tushy. This side of the battery is positive, this side of the battery is negative. So if I have current, and we'll start talking about current on Friday, and we'll start talking about resistance on Friday, but if I have current, current is going to go from positive to negative. So that would be the direction of flow that I have in my system. So that my current goes from positive to negative. But we know what's moving in my wire is actually the electron, so Ben Franklin got it wrong. Okay? So just be aware that we're going to start dealing with this, and Ben Franklin got it wrong, and even though we deal with current like this, that's not actually what's physically happening, and we start that discussion on Friday. So what I have here is I can think of a battery, and what my battery does is we've already talked about that my battery is filled with electric potential. So my battery is filled with electric potential. My battery is also filled with charge. So my battery has charge in it. It's also got my electric potential associated with it. And I can go in and deal with my battery. We define that this lovely device, as having what we call capacitance. And that's what we defined, and we said that capacitance of this device was going to be whatever the charge stored on it divided by the potential across the plates. Okay? The charge stored on it divided by the potential across the plates. So basically what's happening is this. I draw my plates. So I have my plates here. This would be connected to my battery, and I'm actually going to draw the battery like this time. So there's my battery. This side is positive, this side is negative, and they're connected. What's going to happen is the battery, we can also look at it as a charge pump. I'm going to put the battery connected here, and this plate is going to become positively charged, and this plate is going to become negatively charged. And it's going to store charge. Now, it's going to take a little time to store charge because the charge has got to get from the battery to the plates, but eventually the charge on the battery is going to get there. So we actually look at that piece, and if I want to go ahead and derive this, if I look at my battery or my capacitor, I can also draw a symbol for a battery that looks like this. So here's my capacitor looking at it side on. I've got an electric field that gets generated in here, so I get my uniform electric field. And that's positive, and that side's negative. And if I look at how we get here, the electric field is looked at the change in potential divided by the distance. So this distance between the plates impacts my capacitance. And that's just a function of how that works. So I get that, and remember that my potential is equal to my potential energy divided by charge. So we had those pieces there. So what I'm going to do is I'm going to work this a little bit, work this equation just a smidge. And there's a reason why I'm going through all of this again. So I have my electric field times D is going to equal my change in potential. My electric field, if I substitute in here, that's KQ, the charge distribution on my plates, divided by R squared times D is equal to my change in potential. I'm going to put D in there and I'm going to pull Q out. That's equal to my change in potential. This is a constant. This is a function of my device. And that is a function of my device. So that all is a function of the device that we get, and that becomes what we're going to define as capacitance, because if I rearrange this equation, I get my KdR squared is equal to my delta V over Q, but I can flip it over. I get my R squared KD is equal to Q over my change in potential, but this is just a constant, and we call that C. And this is dependent upon the configuration of my device. And that's where we get our lovely capacitance, and that's where, and we said that this is actually done in farads, and this is in charge, which is coulombs, divided by volts. And that gives us farads. So let's make one. Okay, I'm going to make a capacitor. It's really tough. Here are my plates. 2 pieces of aluminum foil. Okay, got 2 pieces of aluminum foil. Even though you can't see it over here because I have it behind there, I've got a really short cable, I have a DC power supply, essentially a battery. Okay, a DC power supply, essentially a battery. I'm going to stretch it over here. And I have my little banana clips are over here, so you can see I have banana clips. So I'm going to be able to connect my plates to a battery. Just happens to be DC power supply. So let's step this over here. Okay, we know, because we've done this and we've had experience of this, that if I connect my 2 plates and I put them on top of each other without something to separate the two, I short circuit the system, right? I totally short circuit the system, it gets shorted out, and I'm not able to get anything accomplished. So I gotta have something to space in between. I'm gonna use a piece of cardboard so that I don't short it out. And so one of these will be the bottom plate. So we're gonna make this one the bottom plate. And see which one that's connected to. This actually is the positive side. The bottom plate is positive. Then I'm going to take the top plate and I'm going to put it over here slightly off so that I can not short it out. And that's the top plate. So I've built a capacitor. It's that simple. Totally built a capacitor. And I can actually look at my capacitor, and so I've got my lovely device here. We can measure capacitance on the device. Let's see if I can get it to zoom in here. Let's see, I'm going to have to turn off lights. That actually shows up a little bit. You can actually see numbers. And my device has a little bit of capacitance on there in the system. So if I hit reset, let's see if I can reset it. And there's just a little bit of a that you'll end up with. And then when you get capacitors in here, when you guys do this in lab, you'll see the different symbols on here. This represents a capacitor. So you'll have that. If I'm doing, these are amps, so if I'm looking at current, this actually gives me current. Ohms gives me my resistance, so when we do this, we get resistance, and V is for voltage, and that'll give me my battery. So we actually have those pieces. Usually when you're using your multimeter, you're going to put your negative one in the common one, and you'll have to kind of keep track of which ones are the other ones when you actually do it in lab. And we've actually connected it to the one that's got my lovely little capacitance symbol over there. And it's giving you, in this case, it's giving you something that's called nanofarads. Now, doing this in here, trying to keep my plates uniform, I need a little help. So I'm going to use a little help here. Make sure that I'm connected. I'm going to use a little help to keep my plates kind of flat. So I'm going to use a box. It's not going to affect my circuit any. It just kind of keeps my plates flat. And I've actually built my capacitor now. I'm going to put a charge across it. And if I look at my DC power supply, it actually tells me that I'm applying 10 volts across the system. So I can actually measure that. So I can go over here, and we don't get anything because I'm not touching anything, and I'm going to actually do it. So here's my positive and negative. I'm going to touch the positive plate over here, I'm going to touch the negative plate over here, and it's showing that I'm getting a little more. Let's see if I'm at there. Yeah, I could be getting 12 volts. So I actually applied 12 volts across my plate. So I'm not shorting it out. I've got my 12 volts over here, and I've got that across the plate. And now I can actually measure my capacitance across the plate. Let's see if I can get it going right there. And I actually get a change associated with my capacitance. So we get no, it's not a big issue to actually build these, and you can build them all the time. And we use them to store charge. So a capacitor is just another way to store charge, and that's how we use them in our devices like camera lights or camera flash issues. Okay, so, but now you're going to get to play with my devices, and we can look up dielectric constants of different materials. And I'm going to switch over to the computer now. Oh, computer, there you go. And now I'm going to switch to our PowerPoint, and this is where we're at in our PowerPoint. So we're going to go from the current slide. I can set up these systems two ways. Now, when you guys do this in the laboratory, think about how my wires are going, okay? Those lines on the chart are wires. So if I'm using the good old banana clips, so I'm going to switch back here and show you the banana clips. Let me get a piece of paper. Okay, so I have a banana clip. I will utilize a couple of other wires to simulate banana clips, but I didn't bring a whole bunch of them over. But I have a banana clip. I have another banana clip. So I'm going to use red to be positive, and I'm going to use black to be negative. So I can put my battery between these two here, so just like my picture. I can put my device, and we'll say that represents a capacitor. I can put my device to look like that. I'll take two more banana clips, and I'm going to have this connected to my device just like that one is. There's my other device that's in here. And I'm going to connect it with my other banana clips. Right here. I'm going to save you some grief when you come to lab, because you're all going to say, I don't know how to put up my little banana clips in order to do my devices. So that is in parallel, because what happens is my charge is going to go through the first banana clips, get here and fill up this one. And And then when it gets a little further along, my charge is going to come in and fill up this one. That's different than if I'm in series. If I'm in series, what I do is this. I'm going to take one end of my banana clip and I'm going to take my other end of the banana clip, and my charge is going to go from here to here. It's going to go from here to here. It's going to go from there to the end of my battery. So my battery is here, and I end up with everything is in series. So think about the path that your charge is going to follow. When it's like this, I'm going to set up like a ladder. Essentially is what I'm doing. I'm going to set this up like a ladder, and my banana clips get attached this way, and that's in parallel. And when I have my things fall through, that becomes in series. So when you start looking at the lab and you're setting up your devices in parallel and series, you're creating a picture that looks very much like this. Let's get there. Just thinking about it. It's not there. All right. So that's in parallel. So when I fill up my charge in parallel, what's happening is the charge is going to go into one and it's going to fill it up, and once it's filled up, it's going to go into the other one. So if I do my measurement from here to here, it's going to look just like whatever the battery is that I have. Same which one there, these are all going to have the same potential across them. So when capacitors are first connected in the circuit, the electrons are transferred across the plates. We get the plates. One plate becomes positively charged, one plate becomes negatively charged. The flow ceases when the capacitor is full. Not when the capacitor is full, and the voltage is going to maintain the same as that of the battery. And that's when we start and we can look at the different pieces. So I can look at the equivalence of the capacitors. Okay? So each has the same voltage across. The total charge in the system is equal to the charges across the capacitor. Total charge is equal to the charge across the capacitor. So I can turn around and give me an equivalent capacitance. And that's an equivalent capacitance for the whole system. So if they're in parallel, you just add up the capacity, the capacitance for each one. If it's in parallel, you just add up the capacitor for each one. Essentially, this is what you're doing. So I'm going to do it again. I'm going to switch back to the document camera. So basically what happens is this. We say that the capacitance, we've said that my capacitance is equal to Q times my voltage. We said that when I'm in parallel, that the charge total is equal to the charge 1 plus the charge 2. So I'm going to rearrange this right here. I'm going to rearrange this, so I'm going to get Q is equal to the capacitance times the voltage. Q is going to equal the capacitance on 1 times the voltage on 1, Q total. Because I could substitute that. There's my Q2 is capacitance on 2, voltage on 2. But we said the voltage on 1 is equal to the voltage on 2, which is equal to just a voltage. This can equal Q or C total times voltage. So I end up with C total, which is what we call C equivalent for the system, is equal to C1 plus C2. And I'm going to do my V here, my voltage, voltage, voltage. So all I've done in this case is just factored out my voltage. These all cancel out. So C equivalent is equal to C1 plus C2 when they're in parallel. When they're in parallel. We're going to find that this is going to get a little confusing when we throw in resistors. But my equivalent capacitance for when I'm in parallel, I just add them up. So if I have a system that looks like this, here's my battery. Let's say that this has a capacitance of 6 microfarads. This has a capacitance of 3 microfarads. The equivalent capacitance of the system is going to be 3 microfarads plus 6 microfarads gives me 9 microfarads. And that's just because my system is in parallel. Well, things are a little different when I go to put them in series. So now I'm going to set them up like this. Give it a second, just thinking about it. Now I'm going to set them up like this. They're in series. When I'm in series, the magnitude of the charge must be the same on all the plates. So my potential difference across each one of those capacitors is going to be a little different. This time, my charge is what happens, where I'm going to be. My charge is what's going to give me there. So the charge is going to be summed up, and my total, and what I'm going to end up with is something that looks like this. So I'm going to go ahead and do the math this time first, and then show you the pictures. So what we just said was this. What we just said was this, that when I'm in series, here's my battery, that this becomes positive, this becomes negative, this positive, this is negative, this positive, this negative. Things are going to go here. If I measure the voltage across here, that's one measurement. This charge here and this charge here, those have to be equal. So what I end up with is that those two charges are equal, but my change in voltage is going to equal my change in potential across 1 plus my change in potential across 2. Now I get Q divided by my capacitance total is equal to Q divided by my capacitance in the first one plus Q divided by the capacitance in the second one. Because all those charges have to be equal. I can divide Q by both sides and I get C total is equal to 1 over C1 plus 1 over C2. Your common mistake when you actually work the problems is you forget to do the inverse over here. Your common mistake when you get to do the problems is you forget to take care of the inverse. So you want to make sure that you worry about, and this is when I'm in series. So this C total is going to equal C1 plus C2 when I'm in parallel, and my total is going to equal 1 over when I'm in series. Think about it. All right, so we get those lovely capacitance. So here it is in words. But we're going to get the charges. The charges are going to evenly distribute across the system, and we end up with it. And then I get my equivalent capacitance. So I end up with that 1 over C is equal to 1 over C1. And we can do this for multiple capacitors. You can do it for multiple capacitors in any combination. One other thing that we have to deal with in terms of my capacitors is we can look at the energy stored. And the energy stored, and we can be rewriting it, we can be rewriting it in a variety of forms, but the energy stored in my capacitor is going to be 1/2 the charge times the potential difference across. And then I can write it also in terms of capacitance, just using that C is equal to Q over V. So that's the energy stored. So you'll have some problems that are dealing with just calculating the energy stored in a capacitor. So I'm going to do one problem real quick so that you guys have all of that. And then Friday we're going to start on to resistors. And that keeps us going. So I'm going to give a system that looks like this. And this is how we do them. So I'm going to draw my circuit, and my circuit's going to look like this. So I have a capacitor here. I have a capacitor here. I have another system here. I've got a capacitor. I have a capacitor. Here's my battery. All right, this one's 6 microfarads. This one's 2 microfarads. This one is 5 microfarads. This one is 3 microfarads. This one's 8. And this one's 3. And I want to know the equivalent capacitance of the system. I want to know the equivalent capacitance of the system. Okay, remember that C equivalent, if I'm in parallel, is just going to be the sum of the different capacitors. C equivalent, if perpendicular, goes as 1 over C EQ is equal to 1 over C1 plus 1 over, that's not perpendicular, that's in series. Okay, C2. So those are my two equations that I'm going to use. So the first thing that I'm going to do is I'm going to break out, I'm going to do the systems that are in parallel first. So I'm going to do this one first. That's going to be 8 microfarads plus 3 microfarads gives me 11 microfarads. I'm going to come over here and do this one. This gives me 6 microfarads plus 2 microfarads gives me 8 microfarads. And then I'm going to do this one. And that's 5 plus 3, so this becomes 8 microfarads. So now I can redraw my circuit. I can redraw my circuit, and when I redraw my circuit, I'm going to have a capacitor. I'm going to have a capacitor. I have my battery. I have my capacitor. And this one is now 11 microfarads. This one is now 8 microfarads. And this one was 8 microfarads. So these two, let me scroll out. Those two pictures are equivalent. That if I've built a device, they're not going to, and I can develop the device this way or I can build the device this way, they're going to work the same. So I have those capacitors there. So now I do 1 over CEQ is equal to 1 over 8. This is microfarads plus 1 over 8 microfarads plus 1 over 11 microfarads. You can do the least common denominator gig. And so now I get 88 on the bottom, right? Because 8 times 11 is 88. So this one is going to be 11 microfarads plus 11 microfarads plus 8 microfarads. So that gives me 22 plus 8 gives me 30 divided by 88. This is 1 over CEQ. Now I can flip it. CEQ is equal to 88 divided by 30. And did I happen to bring in? I didn't happen to bring in the number. So whatever that is in the calculator, and I did bring my calculator, so I can actually multiply it out. 88 divided by 30 gives me that this is 2.9 microfarads. And that would be like redrawing the system to look like this. I just have one capacitor in the system. and now that would be 2.9 microfarads. And you guys will get to play with these in the lab. Now, for the lab, I think the lab does both capacitors and resistors. And when you guys do it for resistors, and we'll get there, and I'll show you, resistors in series, so a resistance in series is adding the resistors. Resistors 1 over the R equivalent is for when I'm in parallel. When I do it for resistors. And we'll get there either Monday or Friday or Monday. Alrighty, guys. You guys okay over there in Enid?